Oscillations is a chapter that has real practical impact on many other stuff that you do in physics. Because this chapter is followed by waves, which you do in semester 2. And if you have to understand waves, you have to know the full meaning of oscillations. So, and light travels in the form of waves. Sound travels in the form of waves. You have electromagnetic waves. I've given you 3, right? So you can see the impact that this chapter is going to make on semester 2. Like if you understand this chapter nicely, semester 2 is going to be that much easier. Now, oscillations, we see it in daily life, but I want to start with something that you don't really see. And I like the PowerPoint that this chapter has presented me with. So it talks about the Comcast building in Philadelphia, which is 305 meters tall, really tall. And at this height, what will happen is if there is a slight shake of the earth, like let's say there is a tremor, like an earthquake, not a real bad one, even a small shake, you know what can happen? Because the base is fixed, the top is like free, isn't it? So it's like a pendulum hanging there, and that can cause a big oscillation at the top. So if you don't do anything to counterbalance that oscillation, the building can just snap and fall, being that tall. So what do? There are different types of things that you can do to counterbalance it. What is done there is you see a 300,000 gallon reservoir of water. That's a huge one. On top of the building, right there. You see that? Right there. So what happens is when the building, for example, goes to the left or to the right, as shown here, to the right, the liquid will move to the left, trying to counterbalance it, Can you imagine what? So it kind of counterbalances that and tries to keep equilibrium. Isn't that interesting? So that is one thing about oscillations that I thought will catch your attention, because we never think about such stuff, But what we think about is usually music, guitar strings. You play the guitar, pluck the guitar string, it oscillates, right? It oscillates. And we know that each string has a definite thickness, radius, different radii. So they oscillate with different frequencies. And depending on where you pluck the guitar, not pluck, you hold your, fret? No, fret is, okay. So where you hold it, you're changing the oscillating length. Come on. And when you change the oscillating length, the frequency again changes. So don't be, don't get worried too much. Just know that this is an oscillation. A violin, a guitar. He was playing music the other day, good music. Anyway, so all these are oscillations, vibrations. But we will mainly focus on the oscillations of a spring. We'll be spending a lot of time on looking at the oscillations of a spring. So let's get started. Oscillations of a spring. It could be a vertical spring, or it could be a horizontal spring. It makes no difference. We'll come to that later. But just imagine that you have a spring. One end of the spring is rigidly attached to some support there, and at the other end of that spring, you have a mass. Okay, so the mass is M. What is the force? mg. And due to that mass or the force, wouldn't the spring extend? Yes. Okay. What is the formula that relates the extension with some constant? I don't know. I can't. Spring constant. That's right. This is live. Your voices are up there too, so be careful. So F is equal to minus Kx, isn't it? Where K is called the spring constant, X is the extension, and F is the force in the spring. Now you've got to be careful. Well, the force in the spring is the same as the force applied by the load. But what's the difference? The direction. So what's the direction of the force in the spring? Force in the spring. Up. What's the direction of the displacement? Down. Aren't they opposite to each other? Yes. Will that always be the case? Yes. Remember, if you pull the spring down and let it go, it'll oscillate. when it oscillates, right? Wouldn't it oscillate? When it oscillates, every time the force in the spring is going to be opposite to the displacement. That makes sense? Because when the spring gets compressed, the force in the spring is down. See? But the displacement is up. Force and displacement are always opposite. That is why you have the negative sign there. So the negative sign there is important because it shows that force is opposite to displacement. Before we go further, I want to give you some definitions quickly. If you do not disturb the mass, it will be in equilibrium, wouldn't it be? And that position is called the mean position. Mean position. What is the displacement at that position? Is it oscillating? No, it's not. So the mean position, the displacement, x is equal to 0. So I'm not talking about the extension in the spring anymore. You understand that? Yeah, there's already an extension when you put that mass, I know. But I'm not talking about that extension anymore. I'm talking about the mass is right there. You don't disturb it. It's going to lie there. Nothing happens. But now if you go and pull the mass a little bit down, disturb it, pull it down, what's going to happen? It's going to oscillate. When it oscillates, wouldn't it go to a certain point above and to a certain point below? Yes. Now these are called the amplitude positions. Maximum displacement is called the amplitude. So this would be plus A and this would be minus A. A stands for amplitude. That means x can take values from minus A to plus A. Clear enough? What is x? X is the displacement at any time. X is a function of time. While it's oscillating, isn't x changing with time? Yes. Can x be 0 while it's oscillating? Yes. Yeah. X can be 0. X can be any number or any value between negative A and positive A. That's what I'm trying to say. So x is actually a function of time. So now you know what amplitude is. Second definition is time period. Now what do you mean by time period? The time taken for one oscillation. The time taken for one oscillation is the time period. What is one oscillation? Let me show you. If you start from the mean position, you go up, that is 1/4 of an oscillation. Come back down, half. 3/4 of an oscillation, 1. So one oscillation is made up of 4 parts, as you can see. And each one takes 1/4 of the time period. Because the time taken for one complete oscillation is called time period. And the symbol there, which we're going to use for time period, is T, caps T. Of course, in seconds, right? Yes. Time, seconds. So let me give you an example. If the time period is half a second, how many oscillations, don't shout the answer out, but put your hand up if you know. How many oscillations will it make in 1 second? I expected more. Some of you need me to repeat it again. If the time period is half a second, how many oscillations will it make in 1 second? Shout the answer out together. 2. How do you get that? Just logic. Half a second for one oscillation, so in 1 second it'll make 2. Now the number of oscillations in a second is called frequency. Number of oscillations in a second. Frequency F is always the reciprocal of T. F is 1 over T. And also T is 1 over F. That's how you get the frequency as 2. 1 over 1 by 2, which is 2. 1 over 2 is 2, isn't it? Yes. And the unit, okay, what's the unit of frequency? Technically, from that formula, what's the unit? No. It's 1 over t. So, what did you say, Sheldon?
1 per second.
1 over second, or second raised to minus 1, isn't it? Second raised to minus 1 is also called Hertz. The name of the German scientist who first created electromagnetic waves in the lab, because of which we have radio and television communication possible. So we honor him. Heinrich Hertz. So Hertz is the unit of frequency, and 1 Hertz means second raised to minus 1. Is that clear? 1 by second or second raised to minus 1 is clear. It is. Understood all the definitions? Now the math. A little bit of math makes it enjoyable. We are going to analyze this motion. Did I hit record? Okay. So we're going to analyze the motion, and we're going to see what math we can bring to it. All right. So here we go. The starting formula is, of course, F is minus Kx. K is the spring constant, F is the force in the spring, and X is the displacement. And I've already told you, X is a function of time. But we do know that force is mass times acceleration, and acceleration is d squared x or d squared y by dt squared. Make sense? And that means that is minus kx. So you can now rearrange this. Just dividing throughout by the mass, you would get minus k over mx. And immediately what should catch your attention is, wow, that means the acceleration is proportional to the displacement. Do you see that? Because on the left-hand side you have acceleration, and on the right-hand side you have displacement, don't you?
Yes.
Aren't both vectors?
Yes.
Both are vectors, which means then again, next you should look at the sign and say, wow. So if there's a negative sign, that means these two vectors are always going to be opposite to each other. Which two vectors? Acceleration and displacement. So that means when the spring is going down from the mean position, x is negative because it's down, while acceleration is up and positive. You know what I'm saying? While if the object is going up from the mean position, displacement is positive because it's up, but acceleration is down, and so negative. So acceleration is always opposite to displacement. Now this type of a motion is called simple harmonic motion. So if this condition is satisfied, it's called simple harmonic motion. SHM. I'll give you the difference. Now if I go crazy, which I am a little bit, and then walk from this wall to the other wall because I'm upset about your grades, and then I time it perfectly, like I take 10 seconds to go from this wall to the other and back again in 10 seconds, am I oscillating? Yes, I am oscillating, but that is not simple harmonic oscillation, because my acceleration is not proportional to my displacement. It's going to be random. My acceleration, but nobody can walk, according to the oscillation of that object under the spring. Try to compare my motion with the motion of the object attached to a spring. Are you visualizing? Come on. Why can't I walk like that? Because how is that block going to move? Let's visualize again. The block, when you pull it down and let go, what's its velocity at the bottom? When just before you let go, 0, and you let go, it's going to speed up, right? Speed up, because the spring is pulling it, and it's going to have maximum velocity when it passes the mean position. Are you with me? Beyond that, it's going to slow down, because at the next amplitude position above, it's again going to stop. You see? Come on. So if you understood, tell me this. At what point is the acceleration maximum? I'll give you a choice. Is the acceleration maximum at the mean position or at the amplitude positions? Now let me try it this way. At what points are the velocities zero? I'm talking about velocity now. That's easier to say. At what points does the object actually stop? At the amplitude positions. Are you with me?
Yes.
So velocities are clear. So where does it have maximum velocity? When it's passing or crossing the mean position. Velocity is zero at this amplitude position and zero at the other amplitude position. But when it's crossing the mean position, that's when it's moving fastest. So I'm trying to say that the velocity is maximum when x is equal to, help me out, 0. Thank you. And I'm also saying velocity is minimum, which is actually a 0, when x is plus or minus a. Yeah, absolute value of the amplitude. That makes sense? That being said, now let's talk about acceleration. The acceleration is right there. The formula is right before your eyes. And so using that equation, you can tell me when x becomes maximum, wouldn't acceleration become maximum too? I mean, in magnitude. Forget about the negative sign. When x is maximum, wouldn't acceleration be maximum? Come on. So can you give me the maximum value for acceleration? Yes, you can. What's the formula for maximum acceleration? I'm waiting. Minus k by m a. The acceleration becomes maximum when x becomes maximum. Maximum, didn't we agree?
Yeah.
And what's the maximum value of x? A. I'm throwing formulas at you. Maximum acceleration is given by minus k by m a, where a is the amplitude, which is when x becomes maximum. Oh, goodness. I forgot to record one whole part. Right, never mind. So, can you take dx by dt and tell me what you get? Dx by dt of that. I'll give you time, I'll wait. Dx by dt is nothing but velocity, you know that, and it is negative a omega sine omega t plus phi. You agree?
Yes.
Because omega is a constant, you got to write it out one more time, isn't it? So that's how. And you know that dx by dt of cosine theta is negative sine theta, right?
Yes.
That's why the negative. All right, go ahead, do one more. So you get the acceleration, which would be d squared x by dt squared, and you would get, what do you get? Minus a omega squared cosine omega t plus phi. Isn't it? Now what you do is you take these two and plug it back into the original equation, which I'm going to highlight. You see, plug it back into this. Plug it back into that. What do you get? Come on.
Negative a omega squared cosine omega t plus phi.
Okay. Plus phi.
Plus km times.
Plus k divided by m. That's what you meant.
Yeah.
X. And x is a cosine omega t plus phi. Isn't it? Is equal to. Right. I just plugged in the values of d squared x by dt squared and x. That's all I did. And one look at this, and you see that you can take out some factors common. I think you can take out a cosine omega t plus phi. Oh, what am I writing? Plus phi. Can you take that out common? And then inside you would have k by, I'm writing the second term first, because the second term is positive. Minus is equal to 0. Stop me if you don't understand. I've just taken the second term and put it first. Is that right? Whenever you have a product, if it's equal to 0, then one of the terms must be equal to, I think I lost you all.
0.
Thank you, Dylan. Now, can this term be equal to 0? If that is 0, then x is 0. Isn't x equal to that whole term? I mean, that has no meaning, no sense. Isn't x a function of time? Can x be 0? Only once in a while, right? Can't be. So you can't say x is 0 all the time, which means there's no oscillation. So that doesn't make sense. So that term cannot be 0, which means k, isn't the wrong thing? Which means k by m minus omega squared is equal to 0. Correct? Which is omega squared is k by m. Which means omega is square root k by m. Omega square root k by m. Okay, finally, here is it. Does anybody remember the relation between time period and omega? Time period and omega in circular motion. One of these days we'll have a final exam without the formula sheet. Not this semester anyway. So t is equal to 2 pi by, you still don't remember, omega. T is 2 pi by omega. And just now we got the value of omega, which means you can put 2 pi by square root k by m, which means you can flip it and write it as 2 pi square root m by k. Can you? You got a very important formula. This is going to be one of our labs, which also means that you can find the spring constant by finding the time period of oscillation, can't you? Yeah. Find the time period of oscillation, you can get the spring constant. How does the time period depend on the mass? If I quadruple the mass, what happens to the time period? If I quadruple the mass, what happens to the time period? If I'm not getting answers, then there is something seriously wrong, maybe with me, I don't know. If I quadruple the mass, it's the third time, it's on YouTube. If I quadruple the mass, that's the fourth time. And I heard him say the answer like 3 times now already. If I increase the mass 4 times, the time period would double, correct? Would double because it's under square root. What if I increase, double the spring constant? What happens to the time period? Does it increase or decrease? Because spring constant is in the denominator, right? You increase the denominator, time period increases. So, if we compare the spring underneath the car with the spring in a ballpoint pen, which one has a bigger spring constant? Under the car. It's so much more tougher to elongate that spring. And so if you set both of these into oscillation, which one will have a bigger time period? The car? The K is so big. You mean to tell me that you want your car, when it falls into a hole in the road, to go like that? Up and down, slowly, so the time period is so slow that you all have back problems at the end of the journey? No. We're looking for suspension springs that can damp it. See? That means we want it to quickly absorb it. In fact, we don't even want it to complete one oscillation. See that? We want it to go take the shock. See? We are going to talk more about that. That's damping. We use it. I can't even think of machines, not many, that do not have springs in them. A spring is a wonderful innovation. It's all over the place. We've been talking about those oscillations and all that stuff. Is that formula clear? Very clear. Any questions on that? No. Let's talk about the energy involved in motion. We're still talking about a spring, mass attached, oscillating vertically. Tell me, what are the types of energy that you can think about? Come on. Isn't it moving? So it has kinetic energy. And the spring always has its energy, potential energy. What's the formula for potential energy of a spring? Oh, potential energy of a spring. Thank you. 1/2 kx squared. And kinetic energy is, of course, 1/2 mass times velocity squared. And the energy is oscillating. Wait, I want you to be listening now very carefully. At the amplitude position, visualize, at the amplitude position, what's the velocity of the object? That means the kinetic energy is 0, right? Yes. But isn't that the position when the spring is either most compressed or most elongated? Yes. That means all the energy now is potential energy of the spring. Correct? Yes. Because the object has stopped, but the spring is most compressed. All the energy is in it. And then when it comes back down, all that potential energy changes back into kinetic. Do you remember that the maximum velocity is when the object is passing the mean position? You remember that? That means that's when the kinetic energy is maximum. What is the potential energy at that point? You see how the energy is changing? So if you know the meaning of conservation of energy, you will understand this. 1/2 kx squared plus 1/2 mass times velocity squared should be a constant. Isn't that the principle of conservation of energy? Yeah. All right, if you understood that, you are going to answer the next question. And it won't come so easily unless you understood. Give me a formula for total energy of a simple harmonic oscillator in the simplest form possible. Give me a formula for the total energy. Don't tell me that it's the sum of these two. Because then you're giving me, look, if you tell me that, then you're giving me two variables, aren't you? Aren't x and velocity both going to change? Right? Yeah. I want, because we know that the total energy is a constant, isn't it? Look at me now. Isn't the total energy a constant? Okay, so I want a formula which has only constants in them, is what I'm looking for. You understood? Because if the total energy is a constant, then the equation must have all constants in them, correct? Because it's a constant. I'll give you time. I'll give you 2 minutes. You please tell the class how you got it. I mean, your way of thinking. Correct. That's all. At the amplitude position, the velocity is 0. So there's no kinetic energy, correct? And at the amplitude position, x is equal to a. X is a. Are you looking at what I want you to look at? The formula now? This term became 0. And this x became a. Therefore, the total energy in simple harmonic motion is 1/2 k a squared. Wrong pen, but it's okay. It works. 1/2 k a squared. Are all those constants? Yes. Amplitude is a constant, okay? Some students have a problem with that. We are talking about where there is no damping, no air resistance, no friction. Amplitude is going to be a constant. Every time it will come back to that same point. All right. So if we draw a graph for energy, how is the graph going to look like? I will let you draw a graph, or one or two, with displacement on the x-axis. This is x is equal to 0. This may be x is equal to plus a. and equally out here, x is almost equal, right? X is equal to minus a. How will the graph of kinetic energy look like? Where is the kinetic energy maximum again? Where's the kinetic energy maximum? When it okay, and remember this is 1/2 mass times velocity square. So it's not a straight line. It's not an equation for a straight line. Therefore, it will look something like this. I'm going to try. Ugh. That's why I don't want to do this. But you know what I'm getting at? Don't laugh at me. Just draw it. Now you know why I draw all this. This is, I'll blame it on the slippery surface. But I can't give up because Miguel is laughing at me. There you go. Okay, that's the graph of kinetic energy. Can you draw the graph of potential energy? You have 30 seconds, not more. Graph of potential energy. Do you know where potential energy is maximum? Yes, you do. Do you know where potential energy is 0? Yes. So your graph should look something like should be more U-shaped, but is that making sense? All right, if that's the case, what can you tell me about this point? Everybody look at this point, or this. What's so important about that point, or those 2 points? That's where the 2 energies became equal. Can you find x when they are equal? Tell me, go ahead, find it. Find x when the potential energy is equal to the kinetic energy. All right, the answer was in the question. The question said, when are they equal, right? Okay, so you put them equal to each other. 1/2 k x squared is equal to 1/2 mass times velocity squared. Is that what I meant? When is the potential energy equal to? And then the halves go away, and we're looking for what? X. But there is a problem right there. X is in terms of velocity. So this is what I'm going to do. With your total attention, I am going to get an expression for velocity in terms of x. Are you with me? We already have it, in fact. We have it. We do know that velocity is, we took x as a cosine omega t plus phi. Remember that? And when we took the first derivative, we got velocity as dx by dt, which is minus a omega sine omega t plus phi. And I know I've not spoken about phi yet. I'll soon do that. It's like a suspense. Is that what we got for velocity? Yes. All right, now is the time. Just assume for this time that phi is 0, because phi is called the initial phase, and it can take any value. It's called the initial phase, okay? It can be anything. Just assume it is 0 now, to make it easy. If it is 0, look at this diagram carefully. Look at this diagram carefully, and this is now circular motion projected. You see this is rotating with constant angular velocity omega? Okay. Do you know that this point would have been where the shadow is? When the object is here? Yes. Right? Yes. Okay. So isn't that the displacement? Because when the object is here, the shadow is going to be right here. Come on. Yeah. So it's moved. The shadow is moved from here to here. Are you with me? So that's the displacement Don't worry about the negative and positive and all that. But if you look at that, isn't this the radius of the circle? Wouldn't that be the maximum displacement? Which is A, correct? That's why I called it A. So if that is x and that is A, isn't this square root A squared minus x squared? Because that's a right angle triangle. And I've just played with theta there. I've assumed this is theta. If that is theta, what is sine theta? If that is theta, what is sine theta from that triangle? Oh, did you know that omega is theta over t, which means theta is nothing but omega times t? So which means this is theta. And we already said phi equal to 0, isn't it? So when I ask you what sine theta, you're looking for sine omega t, sine theta, which would be opposite side by hypotenuse. So come on, anybody here? Sine omega t would be root a squared minus x squared divided by, all right, take that, plug it back here, and you would get velocity is minus a omega root a squared minus x squared by a. And you go cancel the a's, you have the formula that we're looking for. See what I did? Simple substitution. So what is the formula for velocity? Velocity is negative omega root a squared minus x squared. That's it, isn't it? All right, so don't forget what we were looking for. What were we looking for? Okay, so go back to this relation, and I'm going to plug that into that relation. So what do I have now? I have k x squared is equal to m velocity squared. So what can I substitute now? Can I say omega squared, a squared minus x squared? Come on. Right? And which means, watch. How do I cancel k and m? Because they're equal. You forgot that omega is root k by the mass. Do you remember that? Did we get that? Not so long ago. Which means omega squared is, which means k is k is the same as m omega squared. Can you let me please cancel those two with your permission? Thank you. So now we got, what do we have? Nothing? No. 2x squared is equal to a squared. Where did I get the 2x squared from? Because there's a negative x squared. I take it to the left-hand side. Wouldn't I have x squared plus x squared? That is 2x squared. So what's x? X is equal to a by root 2. Yeah, because x squared is a squared by 2. Isn't it? Yeah. And then take the square root on both sides. X is square root of a squared is a, and then square root of 2, which comes out to be 0.7071 of x. On your calculator, try 1 by square root 2. That's a term that repeats in physics many times. The 1 by square root 2. Semester 2, it will come back about 5 times. It's 0.7071. Okay. Take a look at what I've been trying to tell you. Look at this point. Is it halfway through? Does this point, this is the x. Remember, this is x? Is that halfway?
No.
Half would be somewhere here, wouldn't it?
Yeah.
So you can see that though drawn approximately, it's like more towards 3/4 of the way. Do you see?
Yeah.
That's what we just proved now. This was a question on the exam one time. Not many did it because we didn't have that before. Now, if I ask you this on the exam again, I'm sure most everybody will do it. But that's nothing. I have to ask you something new. So I see if you can think and plug it in. Here is a short review of what we've talked about so far. So you can really focus. In 5 minutes, this is what we talked about. I did define simple harmonic motion. Did I?
Yeah.
I said 2 conditions have to be satisfied for any oscillation to be called simple harmonic. And those 2 conditions came from this formula that we derived. You remember? And the conditions are, the acceleration must be proportional to the displacement, condition number 1. Condition number 2, the acceleration is always opposite to the displacement. How do I know it's opposite? Because there is a negative. And then rearranging that, we got an important relation. Omega is root, what was it? K by, right? That was one of the first equations that we got. And then we went on and found that the time period of oscillations of a spring, a loaded spring, is this. And we've been talking about vertical oscillations of a spring. Let me just add something to this. What if I have a spring set here? A spring is set here, and assume that this surface is frictionless. And there is something here, so I can attach one of the spring to that. And then there is this block of wood, and I pull it here, it's going to oscillate here, right? These are going to be horizontal oscillations on a frictionless surface. Agreed?
Yes.
Can we use, or could we use this same formula to find the time period of oscillations in that case? Or is this only applicable to vertical oscillations of a spring, is what I'm asking. Now, if you give me the answer that this is only applicable to vertical oscillations, then I would ask you, look, the acceleration due to gravity is not in the picture, although this is vertical oscillations. Do you notice that?
Yes.
So it's like the gravitational force had nothing to do. And you're like, what? Yes. You know why? Because it cancels itself out. It tries to pull the mass down, but when the mass goes up, it opposes it, doesn't it?
Yes.
When the mass comes down, the gravitational force is like, come on down. When it goes up, what does the gravitational force do? Cancels out. So do you see that it cancels itself out?
Yeah.
Okay. If that's the case, if the gravitational forces had nothing to do, then for sure this can be applied even for horizontal oscillations. So this is the formula for oscillations of a spring, whether it's vertical or horizontal, as long as there is no friction or other damping forces. Damping means opposing forces. Opposing forces. So no friction, no air resistance. You know, we're talking about an ideal thing. It doesn't happen in practice. So next class we'll talk about the real stuff. Because ideally, you can say, hey, there's no friction, no air resistance. But in practice, there will always be. Correct. So we have to improve on what we're doing now and bring in damping. That's going to make it more interesting. But before that, did we get a formula for displacement? Cosine omega t plus or minus phi. But what if I wanted to write x is equal to a sine omega t plus or minus phi? Would that be okay? What is the difference between a sine function and a cosine function? The shapes are exactly the same, except that one is 90 degrees different from the other. Sine 0 is 0, cosine 90 is 0. You see that? So there is a phase difference. I hope you're listening. There is a phase difference of pi by 2 radians between them. 90 degrees, pi by 2 radians. Now I'm telling you what phi is. Phi is called the phase difference or the initial phase. Initial phase. It could be anything. It depends on where you started timing it. Look, if you start timing it when at A, you're perfect. Because isn't that when the shadow is exactly at the center? But you know how we are. We might start timing it when it's here. So that means there is already an initial angle. See? Isn't there already an initial angle? That is what I call phi. Hopefully you understood. But that angle is not going to change thereafter because it's only the initial condition of motion. What if somebody started here when it was at B? What is phi? Pi by 2. What if somebody started when it was here? Pi. You know what I mean? What if somebody started one rotation later but started exactly at A? You know, one rotation late but exactly at A. What's phi? Or 0. It's the same thing. 2 pi to be perfect because it's already complete on Oscillate. That's what I mean by velocity. All right, I skipped. Now what about the formula for velocity? Did we get a formula for velocity? Give me that formula. Omega root a squared minus, actually there's negative, isn't it? Yeah. Do we have a formula for acceleration? Oh my goodness, it's right here. Okay. Look at the formula for velocity and tell me the formula for maximum velocity. Look at the formula for velocity and give me the formula for maximum velocity. All right, so everybody's looking here. When would that term be maximum? When x is 0. So just put x is equal to 0. What do you get? Whatever you get would be the formula for V max. What do you get? What do you get? A. Right? Because when x is 0, it's passing through the mean position, isn't it? Okay. Can you give me the formula for maximum acceleration? Huh? When is the acceleration maximum? In magnitude. When x is maximum. Look at the formula. When x is maximum, isn't it? Yeah. We're looking at this formula now. Acceleration is maximum when x is maximum. What's the maximum value of x? Okay. So put it, you got the formula. Minus omega squared a. You try cramming all these formulas, it's tough. You try understanding, you get it. You know, like you can go from one to the other. You make that connection. This is what we did, and then we talked about energy. Did we talk about energy? Yeah, we did. Okay, give me the formula for total energy. Total energy was 1/2 k a squared. All right, what is the total energy is made up of two parts, the potential energy of the spring and the kinetic energy of the mass. So separately, there would be 1/2 k x squared plus 1/2 mass times velocity squared, which we know should be a constant, which is this. Is that making sense? Yes. Even with that formula, you can get a formula for velocity. Whew. Just put it there, you will get a formula for velocity out of that. You get the same formula we got before. Does anybody see that? If you put, wouldn't the halves cancel out, and then couldn't you rearrange and get a formula for velocity? You would certainly get the same that we got before, except we won't get the negative sign. Would we? No, we won't get the negative sign. Yeah. So that's what we talked about so far. Okay, so you know what this talks about, right? Yes. Oscillates between this minus a and plus a. Do you know what this is? by any chance? Do you see that it's at different times? You can't read, neither can I, but it's at different times. You know, it's like 0 time, quarter of time period, half time period.
Yeah.
Or it's better to point here. That is at 0 time. Oh, sorry. That's at 0 time, and here it's after quarter time period, half a time period. Are you with?
Yeah.
But do you recognize that waveform? That's called a sine wave. Or a cosine wave, of course. Both have the same shape. All right, take a look at this. It's the graph of position and time. Does it make sense?
Yeah.
At 0 time, where was the object? That's because we are using a cosine function. What is cosine 0?
90.
I mean, what is its value? Cosine 0. 1. No, cosine 0 is 1. That's why we start from the amplitude. This is 90. What is cosine 90? 0. This is cosine 180. How much is cosine 180? Negative 1. This is 270. What is cosine 270? 0. What is cosine 360?
1.
Do you see? Do you recognize that that's one oscillation?
Yeah.
What if we had used the sine function? Would it have the same shape? Yes. But where would it start from?
Sure.
Start from the 0. You got that? Okay, very good. We're talking about a cosine function. That's why the graphs are like that. Oh. You know what this is? This is, you could have a lab like that. Watch. If you have a spring with that mass oscillating and attached to the bottom of the mass, you have a pen. Come on, you have a pen.
Yeah.
Well, if it's oscillating vertically, then the paper has to be moving. No, I can't. If it's oscillating, if it's oscillating up and down, there's no way I can get that waveform unless, how should the paper move if I should get that waveform? Up and down, it should move this way. Is anybody with me? If you have a paper underneath moving at a constant velocity, would I get a waveform like that? What if the paper moves this way?
No.
Will I get it? So how should I set it up so I get a waveform? Yeah, the pencil should go this way, and how should the paper go? Are you with me?
Yes.
So you have a spring and you set it up so that it oscillates this way. If it oscillates this way, then the paper has to go that way. I think I'm confusing everything. Are you getting it? At a constant velocity. So that is what they're showing. That is what is shown there. You know, that's the dots that the pen put on the paper. Oh, what a waste of time.
Isn't an example just in that way?
Yeah, sure. That is what the seismograph and seismograph uses. Man, it's tough here. Anyway, do you see that the phase difference between these two is 5?
Yeah.
Oh, just look at these two graphs. Isn't this one shifted by that much? As compared to this, that's what you mean by phase difference. Okay, that's why I don't use all this. That's a pain and all that. We don't need all that. Position versus take a look at this one time, please.
Double helix.
Do you notice the difference between the position time graph and the velocity time graph? And tell me why. Why are they shaped differently? Like the position starts at maximum while the velocity starts at 0. Come on.
Good velocity.
Because velocity is a sine function. What formula did you get for velocity? You got minus a omega sine omega t plus phi, didn't you?
Yes.
Come.
Yeah.
Are you with me? Okay, what about the acceleration graph? How would it look like? The acceleration time. What was the formula you got for the acceleration? Didn't you go back to a cosine?
Yes.
So would it have the same kind of shape as the position graph? Yes, I wish they had drawn all three on the same. No, that is different. That's what we wrote. That was the shadow thing. They did not. Anyway, never mind. Somebody walked into a church one day where there was no electricity, and you had those long pendant lamps hanging down, and the wind was blowing, and the lamp was oscillating. We can use this to measure time, because the oscillations are like periodic, see? And was born the pendulum clock. I know you may have seen the pendulum clocks, but in our time, we only had the pendulum clocks when I was a teenager. That's in the 60s and 70s. We only had pendulum clocks. We would have a pendulum. You know what a simple pendulum is like, right? And then half an oscillation is 1 second. Another half, another second. So what's the time period of that pendulum clock? 2 seconds. The time period of any pendulum clock is 2 seconds. So each half, 1 second. All right? I will continue the story after this, because I can't finish the story until we get a formula which is really easy to get. We want to find the time period for a simple pendulum. And we are going to get it as 2 pi square root L by G. Are you happy with that? If I throw that formula at you, you're very happy without me telling you how to get it? Francisco is like, yes. No, I'm not happy. So let me tell you how to get that. As this pendulum is swinging, by the by, an ideal pendulum should be made of an inelastic string, should not stretch, and it should be a point mass. Point mass, practically impossible, so we'll substitute as a metallic sphere, a ball or something. So its mass is m, the length of the pendulum is L, and here it's making an angle theta, and it's swinging. Okay, it's swinging. It's going to be swinging this way, isn't it? Right now, okay, let's say that the amplitude is somewhere here. It's going to be swinging between these 2 points. Minus A plus A is the amplitude. It's going to be swinging. I want you to tell me, hey, in the case of the spring, wasn't it the force in the spring that was making it oscillate? The force in the spring? In this case, what is making it oscillate? The tension. What is making it oscillate? Somebody said it. Spencer, say it loudly. Gravitational force. What's making it oscillate is the gravitational force, isn't it? You pull it to one side, let it go, it's going to keep coming back. All right. So, what are the forces acting on it? What is that? Mg. Okay, what are the other forces? Maybe use a different color. Yeah, tension. Tension in the string. Oh, sorry. That's why I don't like this. Tension in the string, which we will for today call Ft. You know why? Because T stands for time period. Ft. Oh, we have a problem there. Are they both along the x and y axis? No. So we will resolve the weight into 2 components. The weight into 2. Ding, 1 component, second. All right, somebody tell me the numbers and we are done. If that is theta, confusing. Let me write this mg. This is mg, isn't it? So what's that red arrow? How much is that? You have mg and you have theta there, so wouldn't this be mg cosine theta? And what would this be? Mg sine theta. Tell me this. Isn't the tension equal to mg cosine theta? Yeah. Tension is equal to mg. But who cares about the tension? We're looking at the motion, right? So which component makes the pendulum oscillate? Right, that's what we're going to look at. So we're going to say, for us, as far as we're concerned, the force is mg sine theta. And of course it's negative, because it's coming down. See that? mg sine theta. Are you with me?
Yes.
Isn't force? I was thinking, I was like, what should I say first? If we do this lab, And if I see you pull this pendulum to one end, because for some people, this is not an oscillation. For them, they have to see it oscillate. They'll pull it to one end here, and they make it oscillate. So if I pass by, I get hit. That may be their idea. But if you do that, you got it all wrong. Because the formula that we're going to derive will only work when theta is small. When theta is less than 10 degrees. Why? I'm going to tell you right now, as you watch, if you, let me name it PQR. Look at this triangle, PQR. In that triangle, is that even a triangle? It is a triangle if theta is small. It approximates to a triangle if theta is small. Are you with me?
Yes.
If you make theta big, it becomes an arc. See?
Yes.
That's where the problem is. So if theta is small, then what is sine theta in that triangle? All right, let me label. Isn't this what you call x?
Yes.
Isn't that the displacement?
Yes.
Because this is the mean position. Come on. Okay, so sine theta is? Nobody talking. I'll wait. Theta is here, theta is here.
X over.
Yeah, thank you. See? Opposite side by hypotenuse. Isn't this the hypotenuse of the triangle? Come on. Yeah. All right. What's on the left-hand side? Isn't it md squared x by dt squared?
Yes.
That is force. Force is mass times acceleration. So can I cancel the masses? And I'm so happy because I just now proved that the motion of a simple pendulum is simple harmonic. Because this is what I got. Isn't this similar to d squared x by dt squared is equal to minus omega squared x? Come on. Isn't that similar?
Yes. Yes.
So what's omega? Isn't that?
You have to do the square root of omega.
Okay, I see what you're saying. This is omega square. Right? Isn't that omega square? So isn't omega square root of g by the length? Right? Okay. So we're done. Someone like, what? Because time period is 2 pi by omega, isn't it? And what is omega? We just got it. Square root g by the length. Can I flip it and make it a multiplication? So now I'll continue my story. I can't forget it because I was the oldest in the family, and every summer our clocks would go slow. Why? Okay, because what you have as a pendulum is a metal. Watch, it's a metal with a disc at the bottom. And the disc can be adjusted. You see that? You can raise or lower its center of mass. So that's the pendulum. What happens in summer as the temperature increases? Expansion. So what happened to the length of the pendulum in summer? Increased. When the length of the pendulum increases, what happens to the time period?
No longer elastic.
It's going to be a little bit bigger. So let's say it becomes 2.001 seconds instead of 2 seconds. So you're like, that's okay. No, that's not okay. Because there's 86,400 seconds in a day, which means it makes 43,200 oscillations. And in every oscillation, it's going to lose 0.001 seconds. So roughly, this is an approximate calculation. 432 seconds is lost in a day. 432,000 times 0.001. Are you listening? You'll understand. That's the difference, right? How many minutes is that? That's like 7 minutes in a day. So if you don't correct that in a week, you have lost 50 minutes. That's gone. You're late. So what I had to do is, because we have to climb up, it's a huge clock, you have to climb up, and adjust the disk to make it go up. You know what I'm doing? I'm moving the center of mass up. But you don't know how much you have to move it, especially at that age. And it's like a game. So you move it. Next day you see that it's 5 minutes fast. Oh, now you go down a little bit. Obviously you move it down, and that's when the parents start, what did you do to the clock? And you have to adjust it according to the radio time, because that's the only source of correct time. You know, the radio, they'll say 7:40. So you have to be listening, 7:45. Ooh. And so it's up and down, up and down. By the time I'm done adjusting, it's winter. I have to start again. Did you get it?
Yeah.
It contracts. So now we don't have all that. We transitioned to quartz clocks and then to atomic clocks. And we never pay attention. Our cell phones automatically adjust, right? You don't have to adjust its time because it's synchronized with an atomic clock. Shows perfect timing every day, every second. An atomic clock loses or gains 0.00001 seconds in 100 years. Just threw that number, but it's really small.
We don't usually base it off the US, I would say April.